Good morning everyone, my name is Replication, and today I would like to give you a presentation about my final bachelor thesis presentation, which is, the name is called Replication of Robotic Telesurgery using a 5G network. How did it all begin? What is the origin of it? What's the final result? Let us dive into it. But before we start, I would like to give you a brief contents that I'll cover today. There will be background, inspiration, objectives, materials, theories, methodology, tests and results, and lastly, conclusion. So let us dive into it. Well, I'm not sure any of you have heard about the news from last year, which says like a Chinese surgeons performed an operation from Italy to patients in Rome, patients in China, in which the distance was like 8,000 kilometers apart, but the latency was just so little as 135 milliseconds, in which it's considered ideal by so many medical terms. So how can technology do this? Well, it started with a combination of two systems. First, it's robotic surgery, and then to make it tele or remote, without any surgeons performed in operating room. So we have to add a bit of advanced communication technologies. So, what's the benefit of it? The benefits of telesurgery is it brings surgical access to the area in which they are active, like surgical care, and then it reduces the risk of long distance patients. For example, if you have to export your patient from Italy to China, it's going to be worse than just do a telesurgery. And then lastly, this telesurgery trend is optimal during the COVID-19 pandemic because it will reduce the contact to mitigate the contagious virus. So what is my inspiration? After I heard the news, I've looked in some places like about the price of real-world telesurgery, but unfortunately, the real-world telesurgery system is cost around like 100 or 200 million dollars, in which is like around roughly 66 million baht or 33 million baht, depends on what brand you're going to use. So it was way too much expensive to be studied by college or university level. And then I looked up and it says like there's currently no available surgical systems or telesurgery system in Thailand yet. So I think it might be interesting to create or replicate one out. So the replication could be much cheaper than the currently on sale telesurgery systems, and we can study about it, like what's to mitigate the latency or to perform a distance operation. Moving on to my objectives. So like I said earlier, I would like to build and create a simple replication of the surgical systems. And then I would like to maintain the connection between two very distant places and minimize the network latency as much as possible. And lastly, I would like to conduct a simple operation using this replication. So this is going to be the material that is used in this project. There will be servo controlled camera, PlayStation joystick, the robot arm, the pick control the scissors, and the robot frames. And moreover, that's going to be the connection part, in which we use the OMADA VPN clients, the router TL-MR6400 and AC access points, the WaveShare RS232 to Ethernet converter, and there will be 5G mobile hotspot and display transit cable and Cisco switch. So let us move on to the next topic, which is about the theories. Well, like I said earlier, in this project, the latency is key, because if you want to do the telesurgery in real world, the latency have to be like so little as possible because we have to do it like, in real time. Like imagine you were playing games and the network latency was just so high, you can't really do anything. Well, this is similar to this because in a real medical term, we have to minimize the latency. And there are four sources of latency, in which there are network latency, processing latency, haptic interface latency, and lastly, search and extraction delay, which the main part is going to be the network latency, in which the latency is going to be like 10 to 999 milliseconds approximately. And this one is going to be a criteria for the latency value for using it in the telesurgery systems. So 0 to 200 is ideal for telesurgery, and then 200 to 400 is suitable, and then so on. And lastly, if you have like 1000 latency milliseconds, it's not recommended for telesurgery. Moving on to how to measure the latency, you may ask. Well, the way is pretty simple and straightforward. You just use the ping command in your command prompt in your computer and just type the address that you want to reach out. For example, ping, and this one is the IP address, and you get the value. But the value here is not the latency yet. As they show here, it's called round trip times in milliseconds. This one is the time where the package was sent to the target and then echoed backward to our location. So we have to divide it by 2 to get the real latency value, in which this case the round trip times was 58 milliseconds, but the real latency value was 29 milliseconds. Okay, let's talk about a real world telesurgery like I mentioned earlier. Well, in the real world, they consist of like 7 components, which are the controller part together with surgeons. In this case, it's going to be me. And then display, haptic controller, and then the network part. And lastly, it's in the robot side, which they're going to be camera, surgical robots, and lastly, surgical systems. So this one is my surgical robots. I say the replication of the surgical robots. So as you can see here, there are IP camera, scissors, and grippers to grab things and cut things across. Then moving on to the controller part. So there will be joystick and display. Well, unfortunately, the haptic controller, as I looked it up, was too expensive, so the joystick was used instead of the haptic controller. And lastly, the core part of this, I would say it's the network part. Well, how does it all work? So if we send some command from the joystick or the controller, it's gonna run through the OpenVPN, through the 5G network, to the internet, and through the OpenVPN server, and then the battery is gone. Okay. Okay, and then from the VPN server back into the robot. As simple as that. And if we apply all these elements into my project, I can say that we can control it anywhere in the world. It's going to be like Thailand to Japan, Japan to the United States, or anywhere. So, well, it's a big word if I say like it can be controlled anywhere on Earth. So we have to find it out that whether I'm saying it's real or not. So we're gonna run some tests. So the robot is going to be stationed at the Six University, and we will do some different place interaction. It's going to be different floor, different place again, and lastly, I will control the robots in Fukuoka, Japan, in which the distance was like 3,700 kilometers apart. Let's look at the first one, in which is in the different floor. Okay, so it's our very good here. As you can see here, the robot was moving according to the controller. Yeah, there was no one controlling it but me, so there was like no ghost or anything else, just me. Okay, and the latency was 25.65 milliseconds. Yeah, this is me. Moving on to 1 kilometers apart. Well, the robots move according to the configuration panel or the display panel. The latency was 42 milliseconds. Then this one is going to be a little bit more interesting. The distance was going to be 25.5 kilometers apart. So we drove to Telesurgery University to find out. So it's certainly in Telesurgery University, and the delay was just 52 milliseconds. So we could say that it's still a real time because the latency was very low. And the last part, well, I flew to Fukuoka and tried to control it, and the distance was 3,700 kilometers, and the latency was just 150 milliseconds. But in this case, the laptop, oh, right. So I was so joystick was used instead of laptop to avoid the transportation risks from the airport or the airplane transportation across. Yeah, it's really controllable, even though I flew to Japan. So this method is pretty worldwide, a combination of 5G and VPN link. One second. Yeah, okay, that's it. And I will try to move some arm. Okay, never mind. And we get the results of this one is a shot that I said earlier. And if you want to look more at more videos, we got the perspective of controller side and then the robot side. So okay, so moving on to the shots. This one is the exponential shot. To plot the value, this one is the distance of 3,700 kilometers. The millisecond, the latency was 150. So according to this, we can analyze so many things. And the R square coefficients of dissemination. So it's basically how accurate our data is according to the trend or the graph equation. So this one is like 0.98, so it's pretty accurate. Then moving on to our conclusion. The surgical robots can be controlled from a distance location, of course. And at a distance of 3,700 kilometers, the latency value was just little as 150 milliseconds, in which, according to our first criteria, it was pretty, I would say it's ideal. And lastly, as the graph is not linear, we can say that the latency is not just dependent on distance. There were like so many more factors for us to discover. And okay, thank you for your attention. But before we start, I would say let us pretend to be surgeons for today, and this is like an emergency case that we have to operate a robot. So, as I said, I'm a surgeon. I will try to control it from different places. This was like a bit of demonstration from our project. Maybe I have to reset it again, who knows. And I would like to thank you all for your attention. Thank you so much.